All right, welcome to Chem 132A. If you're in the wrong place, I suggest you leave with all haste. This is, was there a question? Hi. Anyway, this is the first quarter of the physical chemistry sequence, and we'll mainly talk about thermodynamics in this class. Let's see, how do you spell it here? There's a little bit of stuff before that, and if there's time, there'll be some kinetics at the end. But you know how that goes. I'm this guy named Craig Martens, and you have my contact information. I think I sent out a rough syllabus, and my email has all kinds of phone numbers. You can get a hold of me if you want. So yeah, this will focus on thermodynamics. I want to talk about a few logistical things before we actually start talking about it. The first thing to note is next week I won't be here. So we have, that's the good news, I suppose, but maybe the bad news is there's a more recent version of Craig that will be here, Craig 2.0, which is Craig Murray has graciously agreed to fill in for me. He taught this class last year. And so he's just going to, I hope, cover gases and get that out of the way so we can just get on with thermodynamics when I get back. Also next week, you're all in discussion sections, or have you all successfully gotten into one? Yeah. So we won't hold the discussion sections this week, but then the following week they'll meet. They're not required. I mean, we're not going to take attendance there. There's no quizzes going to be popped on you there or anything like that. And so if you couldn't get into one that you would prefer to go to, and if you go in a space, which probably there will be, then feel free to attend them. More than one, I suppose, would be okay. But if within reason, if it's full for some reason, then you don't belong there. Be mindful of that. Let's see. Grading. Right, you're all interested in that. So the plan is to have 2 midterms and a final exam, and I guess points per hour of labor will be equal. So the midterms will be half the final. So 25%, 25%, 50%. There'll be plenty of problems we give you, and for you to work on and be discussed in discussion section. Solutions will be made. We'll talk about some of the more interesting ones in here probably. But they won't be graded. So all of your points are on the exam. And so that's just sort of the reality. The other option, of course, as I'm sure you've all experienced, is to have electronic homework or something like that. I don't know what you feel about electronic homework, but I think you can waste hours trying to get the answer, but you're trying to get I'm recording this, I think, but Yuja, I think, is recording this. We'll find out later. My plan is to record these lectures and also to provide you with these PDFs of my lectures. So anyway, I have to watch what I say. But the electronic homework, I think, is just more trouble than it's worth. So that means that I guess more is riding on the exams than perhaps in some other classes. What happens when I teach general chemistry? Everybody is obsessed with the electronic homework, but at the end of the day, almost nobody's grade is influenced by it. Why do we assign it? It motivates people to learn something, right? That's the whole idea. But now you're juniors or whatever, third year students. Most of you, maybe beyond that too. So presumably you're adults. So I plan to treat you like that, meaning that you have a subject to learn, and we'll provide the tools to do it. But I can't teach you anything actually. I can make some jokes and maybe help you think about what you should focus on when you teach yourself. But you have to do it yourself. So we'll give you the problems, and I hope you will take advantage of them and work them and then learn that way. And we won't be forcing you to do to do that. But then the exams will come along. And now I'm not planning to drop an exam or something like that. I know one of my colleagues taught this course a few years ago, and he would have 3 exams and drop one. I mean, so I'm not going to do that. But the way I will work out your final grade, using these following ideas. So you're familiar with the process of distillation, right? So you take something and you boil it, and then you make the bourbon fraction that comes out of the stuff that's left behind. So in Chem 1 organic, you have a lot of things that you have to kind of filter out, right? In a way, there's people that maybe they shouldn't be chemistry majors or whatever, but I'm assuming that by the time you get here, you mainly know what you're doing, right? So you're pretty good students. So my intention is that most people will get an A or a B in this class. I mean, that's my audience, right? Now, every time I teach an upper division class, there are certainly maybe more than a few people that insist on getting a lower grade, okay? Don't be one of those people. And so that's sort of the framework of the standards. Although a class like this, it's quite easy to get yourself into trouble if an exam is put in front of you and you have not been keeping up. Then you know that feeling. None of this looks familiar to me. Don't be in that position. When you get an exam to do, it should be familiar to you, because the problems and even some practice questions should be very much in line with what will be on the exam. So it's not going to be one of those classes where you go to the class and then the exams come. Where did these come from? The professor got mixed up when he was digging out his old files, and he gave you the exam for the other class he teaches. Something like that. In some disciplines, you can never even tell this. In chemistry, though, it should be clear. So there should be no surprises when you take the exams. Now, the way the final grades are determined is very simple. I will have a total number of points, and I will sort the points in order, and then I'll draw some lines. But there's always edge effects, right? Boundary effects, bad luck, and so let's say you are just below some line, and I always look below a cutoff and look for anomalies, right? Meaning that, and not dropping an exam, but let's say you did well on the first exam, and then something happened in your life or whatever, and the second exam was a disaster. But then the final was great, and now it's not fair to just automatically say, congratulations, but if that anomaly caused you to miss something, then I will elevate you based on that. So improvement over time is good. A little bad luck now and again. I mean, if it's bad luck on the final, that's worse. But finals always go better than midterms, because whenever I give a midterm, as short and as simple as I make it, most people don't finish it. Right? But when the final rolls around, then lots of people finish. You can do anything in 2 hours, right? You can panic for an hour, and then, get your act together. And, the exam, like the final exam, if you knew what you were doing, it'd probably take 20 minutes of effort, right? I mean, it's not meant to be 2 hours it's not a marathon, right? There's some representative questions that cover the material, straightforward to do. Not lots and lots of calculations. I think it's a waste of time to have 20 numbers that you're going to multiply with your calculator. So the answers will be something like R log 2 or 0. I mean, those are my favorite kind of answers. So if you know what you're doing, it doesn't take any effort to do it. The trick, though, is to know what you're doing. And so anyway, so does that give you a good understanding of the way that the grading will go? Okay, good. Office hours. So there are TAs first. There's 2 TAs. Are they here? Are you here? Uh-oh. Okay. So there are two TAs for this class, and they will be splitting up the discussion sections. And they'll also be doing most of the grading. I may occasionally have some interesting question that I'll want to grade myself. And I'll get to that in a second. But they'll also have office hours. I think one of them likes to do them on Zoom. So whatever you you feel free to interact with both of the TAs, not just the one that's in your discussion section. The more people you know, the better, right? Find them on LinkedIn, do whatever. But anyway, if you like to Zoom with people, you can Zoom with them. I don't like to Zoom with people so much, although I have to say that, it does make life easier when you're lazy sometimes. I do go to faculty meetings on Zoom because I don't want to sit with all those people that are my colleagues. Anyway, but what I plan to do is to find a kind of a public place like the Phoenix Grill. Do you know where this place is? Yeah, it's sort of halfway around the ring. Depending on the weather, I'll probably go there like 9:30 in the morning or something like that, or 9 o'clock, Monday, Wednesday, Friday. And if it's between, and I'll work on my lecture. But if you want to come talk to me, like maybe from 10 to 11, or, Monday, Wednesday, Friday, you can find me there. You can come. People don't like to go to my creepy office, including me. If you visit my office, you'll see what I'm talking about. It looks like a hurricane had just gone through. But anyway, so I like to go to a public place, and then you can, a few people can come and sit. And if you're shy, you don't want to ask a question, but then you like to hear what other people ask. And that's what I plan to do, and I'll give you the details about that when the time comes. So, like I said, there's a little bit of advice about the course and sort of some information about how we're going to do it. Like I said, the homework won't be graded, but there'll be problems to do, and we will discuss them. But like I said, take responsibility for teaching yourself the material. And the book is okay. By the way, here's the book. And this is the 12th edition. They keep cranking these editions out. Why do they do that? Because they want to sell you something, right? They want to sell you the passcode to do the electronic homework. And, an old copy is no good, right? You need to buy a new one. Well, okay, to heck with that. So any edition of this book would be useful. There's different ways that they do the book. They have like a 1-volume compendium of all of Chem, but they've split it into 2. So I don't know what, it's crazy business. Like this book goes from chapter, where is it? Like we go from chapter 1 to 2, and then all of a sudden we're like in chapter 6. Then we go to chapter 16. So they're up to something. But this book, put it in your library. This is not my favorite book, but it's the one that we use. Any book, and more than one book, like look around broadly if you want to really learn it. But this book will be very useful. That being said, it's not absolutely essential. So if I give you problems out of the book, I won't say Atkins 2 point something something. I'll say here is the problem. And so it should be self-contained. Do I, as I don't have to tell you, normally students help me find things online for free. So I'm sure you can, I have on my computer essentially a copy of this book that took me 10 seconds to find. It's not exactly the same book, but it's exactly the same subject. What? Yeah, there's that one. Yeah, it's got this blue. Yeah, that's fine. Yeah, please go ahead. That being said, intellectual property is a very important thing that should be protected, right? And the authors of the book, they put a lot of work in. But then there's the publishers who put out a new edition every week, and they want more. They want more from you. So anyway, okay, any questions? Yeah. The final date is, I don't remember. It's like Friday, 8 a.m., finals week, okay? So that is that good? I don't know. Is that the last day of finals? Okay, so you have to stay to the last day of finals. If this were a graduate class, we would have a take-home final, but I can't. Can I do that? No, I can't. You know, they'll come. They'll find me. Okay, and you know, I don't want to read your Chat GPT answers either, right? And so, you know, we're going to have to do that, and I'm sorry for that because, just like you, I would like to get the hell out of here, right? You know, and but that's the way it's going to be. The exams, though, we can pick a day, and you know, I could pick a couple days, but what often happens is it'll turn out half of you have some other midterm, right, on some day, and I don't want to have them. Do we want to have? You want to have two midterms on the same day? No. So we will do what you'll learn next quarter. We'll orthogonalize the functions so that your exam is on a day that you don't have another. Now, you know, there'll be a few people that'll get mad because they actually are taking some other weird class and they have an exam, right? But we'll set that soon. But do you guys mainly know when you're having your midterms and other classes now? Okay, so when I get back from where I'm going to Colorado for a conference. If I get back, you know, if it snows or something, you never know. But when I get back, we'll set that. Okay. Anything else? All right. Well, you know, there's life is short, and so we should probably start learning the subject. What I'm going to do, though, is Professor Murray, and be nice to him. You know, not because of kindness, but if you're not nice to him, he won't be nice to you probably. So anyway, don't give him a hard time. You guys seem to be pretty calm. He's going to talk about I think they call it focus, right? Focus 1 is what why don't they call it chapter 1? I mean, okay, but I'm going to start with focus 2, which is thermodynamics. And so I'll say what I'm going to say today, try to get the ball rolling, and then he'll come back in. And he'll talk about gases, the ideal gas, kinetic theory of gases, non-ideal gases, and then when I come back, we'll just stop. Okay. You know, it's interesting, it's important, but the most important thing is thermodynamics, because this is really a cool subject. Can I use that word? I should probably say groovy or something, right? But I went to University of Nebraska. I took are they doing well in football this year? I don't know. Not so good. They were national champions when I was there, and when I left, it went downhill. Did I play football? No. Anyway, I took physical chemistry and I took thermodynamics. How do you think I did in the class? I did really well. Okay, I got A. I got it, but I just didn't get it. It made no sense to me. I didn't get the big picture. You know, it was always like, you know, delta H's and delta G's. What are those things, right? And so I never got like the big picture. It was all doing these problems, and the kind of problems I had, it was like you memorize a formula. They give you 20 numbers, and then you put them in the 20 places of the formula you memorize with your calculator, and you get a number. And then if you don't write the units down, you're in trouble. And if you put too many decimal points, you're in trouble, right? So that I didn't like it, okay? And then I finally, when I came here and had to start teaching it, then I sort of kind of started to enjoy it, because it really is it's like the economics. It's the common sense of nature and science, okay? So, you know, there's energy and entropy. Everybody here, have you all heard of entropy, right? Yeah. Yeah, you must have a sense of what it is, right? You know, what would you say entropy is? It's disorder. Yeah, it's disorder, right? So in other words, if I build a jigsaw, my mother-in-law spends her days building jigsaw puzzles, right? So were I to visit her and knock the jigsaw puzzle off the table, it would break into pieces. The entropy of the puzzle went up, right? And so you have an idea of there's energy and entropy, and they're both very subtle ideas. but that's what I'm going to start talking about. We all know what energy is, right? But you know, it took a long time for people to figure that out because it's sort of an abstract concept. They thought like heat was a liquid that flowed through matter. They had no idea that there were atoms. They had no idea that something that was hot. The atoms are moving faster than was cold. But they invented all the stuff that we teach in this class before we really mention atoms. Now, Craig Murray is going to talk about knowing that there are atoms, and I'm going to do that too. But historically, thermodynamics came before people even knew there were atoms. So, kind of an amazing achievement. But it's like economics, you know. So energy, I'll just tell you that we could do the whole class in 5 minutes. It's basically energy is conserved, right? It's like money, right? So you can have a bank, you can put money in, you can put money from one account into it, you can take money from another account. You can go to an ATM, put cash in it, your paycheck can go in, right? And, you know, as long as there's no politicians involved, it's conserved, right? So, right? But then there's entropy. And what that means is the energy is always 100% conserved. The energy of the universe is conserved, you know, like not separate parts, but there's always transactions going on. But there's rules for these transactions. And that's where the entropy comes in. And it's like tax. It's like a tax. You can't do things with energy. You can't just do anything with energy because you can't violate the second law of thermodynamics, which means that at best, if you do something, the system, the universe does not become more ordered. That can't happen. Pieces of it can become more ordered, and this is where things get quite interesting. So you probably have this idea that the entropy of the universe is increasing and order is increasing, right? And you go home and tell your parents this and they, okay, I'll send another tuition check. It sounds like you're learning something. But you knew it already. But, you know, how could we be here, right? So, you know, as the Earth, you know, developed, order spontaneously happened. You know, so we're a lower entropy. You know, as time goes on, we are low entropy. Or like, how can you have a hurricane? You know, so you have the Earth, and then you have the atmosphere, and then all of a spontaneously you get this cyclone. You know, and you know, I hope you can sort of would buy this. That thing is more ordered than the alternative. How can order form spontaneously? Well, you know, the one answer to that is, well, the North Pole is cold, and the equator is hot. And you know, so by the way, happy National Coffee Day. You know, I bring coffee so I don't fall asleep during my own lecture. That's your job, right? But you know, we know that you know, like thermal energy goes from something that's hot to something that's cold spontaneously, right? But if you can take a little part of the universe and have its entropy go down to make that happen more quickly, right? Let's say, and you know there are the principles behind this idea have yet to be fully articulated, but you know it's probably true that if there's a way whereby part of the universe can become ordered, like you can have a cyclone, and that you know, a cyclone is like having a truck driving heat, you know, from the equator to the North Pole, rather than just sort of randomly conducting up there, right? So, you know, like if I have hot molecules here and cold molecules there, there's some warm ones in the middle, and you know, the hot ones kind of collide with their neighbors, and because they're moving fast, and it's like a billiard ball process. Heat will work from hot to cold, but it's not that fast. But if I could get an Amazon delivery truck and put the hot in there and drive it, and then dump it out there, then hot, you know, energy is going from hot to cold more quickly. And when energy goes from hot to cold, as we'll talk about, that increases the entropy, right? As my coffee cup cools, the entropy of the universe is going up, and it's pretty lukewarm now, by the way. But so you can have a piece of the universe being ordered and satisfying the second law. There's loopholes. So you have money and you have to pay. So entropy is like a tax. You know, if you're going to do an exchange, you're going to have to pay some tax to make sure the entropy of the universe goes up. But there's all kind of loopholes. You know, oh well, we can make a ordered patterns, oscillating chemical reactions. There's many things that you can see. You know, like circadian rhythms of just living things in general. You can make all these things while making the entropy of the universe increase, and there's sort of loopholes. So it's kind of interesting, I think. But okay, we're getting off topic. And by the way, we'll do that on occasion. But that sets the stage for thermodynamics. So let's say, let's start. How much time do we have left? Oh, plenty. Okay. Thermo is a game. It's like a game with simple rules. And I basically just told you the rules, right? This is like chess or Go or something, simple rules. But it's challenging nonetheless. So when I teach I'm teaching the graduate thermo next quarter, if anybody's interested. But every time even when I teach this class, every time I teach this class, I learn something. And and usually the way I do it is I make up, oh, this is a good problem to put on the midterm. And so I make up a problem. Then it turns out I don't know how to do it. Okay. I wouldn't have thought this before. So I'll cook these problems up, and then I'll go talk to my colleagues. Can you read? Is the font? The font will be better on the exams. Challenging, nonetheless. It's a big word. I'm sorry. But anyway, I talk to my colleagues, and they don't know how to do it either. You know, so that it's very easy to come up with a very simple problem in thermodynamics that once you see how to do it, it's compelling logic, it's common sense, but it's hard, you know, and you can come to grief on an exam. So I try to make them not those kind of problems, straightforward. Most of the problems will be straightforward. Now, I should have talked about this before, but let me add it now. So there's a broad spectrum of people in this class regarding their relationship with physical chemistry, right? So some of you will want to go to medical school probably. Some of you have to take this class. You don't want to take it. Some of you want to be physical chemists. And so I hope that this class will provide something for everybody, meaning that if you don't like thermodynamics, fair enough, okay? But if you put the effort in, you should be able to get the outcome, right? So you do the work. I don't expect everybody. I don't want to. The last thing I want to do is judge you on how similar you are to me, because that would be. But if you really are interested in thermodynamics versus not, that shouldn't really matter. But if you are, I don't want it to be so pedestrian that it's boring, you know. So there may be a question coming, like one question on a midterm, and I'll put it at the end, you know, so it's obvious which is the one that's tricky. Okay, that's just for those of you who really want to think about it. If you don't get it, it's not going to be the end of the world. And I'll put it at the end because often I've been in this situation myself. I look at a question on an exam, thinking back a few years ago I was taking exams, right? Is this a hard question or not? I have no idea. And normally it's not going to be, okay? But if the last one could be. Oh, and one piece of advice: if you're doing a problem on an exam, and there's a certain amount of space for the problem, that should be more than enough space. And maybe you've been in the other side of this, but whenever I teach classes, you always get that exam where someone is trying to do a problem, and then it goes on the back page. And it fills up the whole back page with illegible calculations. If you're doing that, you're you're barking up the wrong tree. The answer is probably, one or two lines of simple arithmetic. Anyway, okay. Let's get on with it. Let's get back to just sort of sketching these rules. And the first step is to set sort of the stage of terminology. And so the game board for this game of thermo is, we have the whole universe. So this is a stylized way of looking at all the interesting aspects of real life. Steam engines, a steam engine making, boiling water and then using that to move it forward. That's the kind of thing we'll talk about. But the steam engine's in the universe. And then the universe is divided into two pieces. There's what we call the system and the surroundings. And so the steam engine's the system, the surround and the ambient conditions are the surroundings. And we have a few kinds of systems that we can. Oops, we don't need to look at my. I did turn my Wi-Fi off, so you don't have to read all the texts I get from my wife. Why did you leave the? Anyway, but we have to be careful of other things. So, this, oops. Here we go. So, the system and the surroundings can interact, so there can be a flow of things from system to surrounding. And that's sort of the game we're going to play. And so there are sort of three main kinds of systems. There are open systems. And here we have matter and energy can cross. Let's define this thing. What is this thing? This is the boundary. That's the wall, the big beautiful wall between the system and the surrounding. Okay, so is that wall? Does it allow the passage of energy? That particular one? It certainly does allow the passage of matter, right? So there's no. That's an open system, right? And a scientific example would be like a permeable membrane. Something that conducts heat through it. Like my cup. So my cup is not. Ideally, it's not, right? The liquid can't get out, but thermal energy can get out. There's a closed system. And that one has only energy, no matter. So if I say we have a closed system, in the language of this game, it's not like closed might sound like nothing, right? But closed to us means thermal energy can get through it, like the walls conduct heat, but no matter can get through. And then there's what's an isolated system. No exchange of any kind. And of course, there's all kinds of interesting, details. Like there's the cell membrane that allows water to pass through because of aquaporin channels, but protons can't get through except if there's an ATPase molecule that's using those protons, to the gradient of protons to make ATP. So there's all kinds of variations on this theme. Okay, so I used a term. We know what matter is, like molecules, but energy, I think I mentioned, we all have our idea what it is, but it was a relatively recent invention, and Atkins and his co-workers define it capacity to do work. Now, I I don't, you know, I don't, I'm not going to give you an exam question. Give the definition of energy, and if you don't say the capacity to do work, you're not memorizing, some scripture or some poems or whatever, right? So, but I do sometimes on exams ask you to explain something simply, because like what is enthalpy, right? So you do all these delta H, that thing you write from general chemistry. This is the kind of thing I could not have answered this question when I was your age, right? But I have more idealistic goals. But if you're doing problems with enthalpy, you might want to be able to say in one sentence what it is. Now, there's not one sentence that answers it, but it's I'll tell you what it is. Enthalpy is a change in enthalpy is a change in energy at constant pressure, right? So the pressure is constant. And like if I'm going to put something in a gas, if I'm going to put energy in a gas at constant pressure, well, the gas is going to expand, right? So there's work being done by the gas. That's the kind of thing we'll talk about. But the capacity to do work is the definition in your book. Don't memorize it, because someone might say, well, what about dark energy? So it's much more complicated, but this is the definition you have. But one important thing, I think, is always pay attention to the units of things, because you can figure out on an exam, if only you knew what the units of things were, you would know that you were wrong, because this thing should be equal to that thing, and their units are not the same. So if I have energy, what are the units? And I'm more of a physicist really than a chemist. I'm a theoretical chemist, right? Which means, I do not like organic chemistry. I said it, okay? But what are the units of energy for a person like me? What? Pascals? No. No, that's pressure. Let's talk later, okay? But, kilocalories are fine, but I like joules, okay? And there's kilojoules, and it's so I assume that you know the relationship between a joule and a kilojoule, and kilojoule, what is that? It's 1,000. It's a factor of 1,000 different, right? So that I'm going to assume, but a joule is a kilogram meter squared per second squared, right? Does that ring a bell? Yeah. And how do I remember? So I've forgotten a lot. I just got my Medicare card, so that will tell. I was born, by the way. So any of you enjoy the horoscope? Read your horoscope. So if you have a certain birthday, that tells a lot about you. Is that correct? So there were two people that were born on August 29th, 1958. Me, and does anybody know who the other one was? No, not that old. No, Michael Jackson, okay? And I remember I was an undergraduate, and I was taking inorganic chemistry, the upper division, and we had to memorize the whole, I'm not going to say it, the whole periodic table. That's what we had to do. This is the Nebraska approach. The state where pi is equal to 3, so the farmers can calculate that rotate those circles that you see when you fly over, because they have the rotating, those irrigation things that are like a thing on an axis, and so you see these green circles and the rest of the square is brown. That's because they irrigate by this arm that goes around like that, spraying water. Well, it's helpful to know pi, right? But it wasn't Nebraska, it was Kansas. Kansas is worse. They were going to legislate it to be equal to 3 or something like that. But anyway, we would read our horoscopes before class, and then I learned that Michael Jackson was born the same day as me. I said, forget about it. but you know, so how similar are our lives, do you think? I can't dance, I can't moonwalk, I've tried. But anyway, I remember this. I remember this because I remember that kinetic energy is 1/2 mv squared, right? And so m is kilograms and v is meters per second. So that every time I write that down, I have to remember this. This is how I know that. Okay, so from physics, you know, the total energy is kinetic plus potential. And you know, there's other kinds of energy, like I mentioned, dark energy, but this is sort of true for thermodynamics as well. You know, like, and it's related to heat, you know, heat and work, which we'll talk about. But you know, if I have some molecules, if I have let's say I have a gas of molecules, right? And for a given and they have potential energy interactions, right? So they interact with each other. And you know, if they're far apart, they might be attracted to each other. But if I try to take two helium atoms and I try to put them on top of each other, you know, they don't like it. They repel each other. So there's some kinetic energy in there because all those atoms are moving around, and I can increase the energy of that thing by putting some thermal energy in. I could raise the temperature. Now they're moving faster. They have a higher kinetic energy. Or I could squeeze them. I could make the volume smaller and smaller, and I could be like Superman, you know, trying to make diamonds out of coal or something like that. I could put so much pressure in them that these atoms are really on top of each other, and they don't like it. Okay, and that would make the potential energy go up, right? And so that's sort of more or less true for us. But in again, getting back to the rules in thermo, we're going to call the energy, and there's other kinds of energies, like the Gibbs free energy. You've heard of that one. But right now we're going to define the internal energy, and that is usually, in this class, it'll be capital U. So that's the internal energy. And you know, thermo is the game of changing the internal energy, and we'll talk about different ways to do that. Now, you know, delta U, you know what this delta means. It's the change in internal energy. And like to simplify, it's again perhaps an oversimplification. But we're in this class, there's two ways you can do it. So the delta U is heat and work. And that's just what I said. You know, I could raise the temperature and keep the volume the same, or I could have it in a thermal bath. So I could have it in a box that would let the temperature always equalize, right? And I could make the volume smaller. So and one way would be to change the heat. The heat would be the transaction of energy. Keeping the temperature the same and making the volume smaller would be work. Okay, so we divide it up that way. And this is we'll be done soon, but not quite yet. This is an important point. Heat and work are not. I'm going to have people wondering what I'm writing again, because I'm going to use a big word. Oops. It helps to spell the big words right. I don't want to highlight it. There we go. Intrinsic quantity. And you know what we'll see later, and I might as well use it now. This is a spoiler. We call these things state functions. See, so my cup of coffee does not have. You can't say its heat is a certain amount. That would be wrong. Okay, but rather a measure, that's a measure of flow or change. So heat is the deposit or the withdrawal. And money, it's like money. You know, like I have a certain amount of money in my bank. I get a deposit. I get another deposit. Netflix takes my withdrawal, okay, or whatever, your mortgage. Things get bigger as you get older, right? And so the amount of money you have is changed by those various ways. And you can say this deposit, it was Q, and that withdrawal was W. Like you did work and you put heat in, like a steam engine would do, okay? But you don't know, the money is laundered, okay? Once it's in your account, you don't say, well, this dollar was this deposit, and that dollar was that deposit, right? It's just all money. And things that are just all money, like your bank account, they're called state functions. And U is one of those things, but Q and W are these transactions. So that's an important distinction. And of course, it's completely different than what people say. Like even saying like this is a hot coffee, right? I mean that almost says like this coffee has a lot of heat in it. And you know, so an engineer might say, well, you know, yeah, we could use this hot coffee to do something and let heat flow out of it, and you know, let that do something useful. But strictly speaking, you know, in the language of this game, that is the way it is. Now, let's see. 3 more minutes, and I will be mindful of the time, so we don't delay you. When I say delta U equals Q plus W, these are from the system perspective. What does that mean? So if delta, like I have a system, okay, delta U is positive, its energy goes up. So I put energy in the system. So Q, if like the flow, okay, the direction of flow, if Q is positive, that means that energy went from somewhere into the system, right? And if W is positive, that means I did work on the system. So I had to do work. I had to have a good breakfast before I did that, right? So this is the convention that chemistry typically uses. And beware, this is good advice in general. Beware of engineers, okay? Are there any that's an exclamation point. Are there any engineers in here? Okay. Anyway, you don't have to necessarily out the engineers. They will write delta U equals Q minus W. So we'll be out in a second. Yeah, give us a minute. Q minus W. Why is this? So we're scientists. You know, we have a sample. We poke at it, right? And we see what it does. We have a certain. This is my theory. We have a certain kind of worldview. Now the engineers, they're outside of the system and they want to make money. Okay. So and you know, it's positive to make money. And so if they can get the system to do work, like if they can get the turbine to do work on the grid, right? And the turbine is the system, they like that. And so they'll use a minus sign in front of the work because they're more interested in positive work, right? But anyway, so yeah, don't make that mistake. This is the convention that we use. And that's enough, right? Because these people seem to want to get in here. And you know, if you have any questions, we're out of time for the questions, but if you have any questions, catch me after the class. And I'll see you a week from Monday. Hi. They'll come. Yeah, I will. Do you want to talk to? Do you want to talk to the team? We got to give you some homework. You know, I think I may ask.